Imagine a gas pipeline valve station 80 kilometers from the nearest town. No reliable grid power, no wired network, no local operator. But the SCADA operator in the central control room can see that valve status right now. They can close it remotely if needed. The device making that possible has no keyboard and no screen. It runs on a solar panel the size of a briefcase. That device is a remote terminal unit. An RTU, remote terminal unit, is a ruggedized field device built for one job: unattended remote operation. The RTU reads local sensor data and transmits it to the central SCADA system via radio, cellular, or satellite. If the communication link fails, the RTU buffers readings locally and uploads them when the link is restored. A standard PLC does not buffer data for link outages. RTUs go where PLCs cannot. RTU, remote and harsh environments, oil pipeline valve sites, power substations, river gauge stations. Power comes from solar panels or batteries. RTU communication is wireless: radio, cellular, satellite. Two telemetry protocols handle most RTU deployments globally: DNP3 in electric utilities and water, and Modbus RTU elsewhere. Built-in data buffering handles link outages. PLC, factory floor, AC power, wired local network, fast local control, no built-in telemetry. The boundary is blurring as some PLCs add cellular modems, but the design intent stays distinct. Field transmitters convert physical measurements into current signals sent over wire to the controller. Unlike the wireless variety, these devices send data on a conductor, not through the air. Pressure transmitters measure fluid and gas pressure in pipes and vessels. Temperature transmitters use RTDs, resistance temperature detectors, and thermocouples to read heat. Flow meters, magnetic, ultrasonic, and Coriolis types, measure how much product moves through a line. Level transmitters using radar or ultrasonic technology measure liquid depth in tanks. Analytical transmitters measure chemical properties: pH, dissolved oxygen, conductivity. The signal follows one universal standard: 4 to 20 milliamps. Take a pressure transmitter measuring 0 to 100 psi. At 4 milliamps, it reads 0 psi. At 20 milliamps, it reads 100 psi. At 12 milliamps, the pressure is exactly 50 psi. The lower bound is deliberately not 0. If 0 were the minimum, a broken wire would be indistinguishable from a valid 0 reading. The 4 milliamp baseline, called the live 0, prevents that confusion. Current signals resist electrical noise over long cable runs. That matters in environments with variable frequency drives and high-voltage equipment running nearby. Control valves throttle flow on a 420 milliamp input signal. In fail-closed valves, the most common configuration, 4 milliamps is fully closed and 20 milliamps is fully open. 12 milliamps positions the valve at 50%. On-off valves operate on a discrete signal, a simple on or off command, no middle values. Variable frequency drives control motor speed by varying the electrical frequency to the motor. Slower frequency means slower pump or fan. Motor starters and contactors start and stop motors on discrete commands. These are the physical outputs of every control loop, the feedback cycle you saw in Lecture 2.4. Field devices are where the digital world meets the physical world. PLCs, HMIs, and SCADA serve one purpose: read sensor data and command actuators. Remove a pressure transmitter and the PLC is blind. Remove a control valve and the PLC has no way to act. These simple instruments are the foundation of every control loop in every industrial facility on the planet. Some are no larger than a thermos flask. This lecture is part of the free Introduction to Industrial Control Systems course. 25 lectures, no cost, link in the description.